Today, we're tackling a massive topic, and I mean literally. We're going to explore the colossal forces that sculpt our entire planet, from the highest mountains all the way down to the deepest oceans. So, let's get into it. Have you ever just looked at a globe and wondered about that? Why isn't the Earth just a smooth, uniform ball? How come we have the soaring Himalayas on one side and the crushing depth of an oceanic trench on the other? Well, the answer is one of the most powerful ideas in all of geology. And here it is. This map pretty much shows you the answer. The Earth's crust isn't one single shell. It's actually a giant puzzle of interlocking pieces we call tectonic plates. And the key thing is, they are constantly in motion, grinding against, pulling away from, and yeah, crashing right into each other. These interactions are quite literally the architects of our world. Right, so these zones of earthquakes and volcanoes you see on maps, they basically carve up the Earth's hard outer layer, the lithosphere, into these huge plates. You can think of them as massive rafts floating on a hotter, much softer layer called the asthenosphere. And it's the slow, churning motion deep within this layer, driven by heat from the Earth's core, that's pushing and pulling these plates all over the place. So the most important part, where all the action happens, is at the boundaries where these plates meet. All the drama, all the mountain building and ocean forming, it all goes down right there. And there are really only three main ways they interact. They can move apart, they can smash together, or they can just slide horizontally past one another. So how about we take a quick expedition to see what each one looks like? Our first stop is a place where new ground is literally being born. We're heading to what's called a divergent boundary, which is just a fancy way of saying a place where two plates are pulling apart. The definition itself is pretty straightforward, right? Two plates are moving in opposite directions. But the really cool question is, what happens in the space they leave behind? That's where things get interesting. That hot layer from beneath, the asthenosphere, rises up to fill the gap. And a perfect example of this is the Mid-Atlantic Ridge. It's this massive underwater mountain range that you can see snaking right down the center of the Atlantic Ocean. This is a huge divergent boundary where the Americas are slowly pulling away from Europe and Africa, causing the Atlantic to get just a little bit wider every single year. So as these plates separate, you get this process called seafloor spreading. Magma from below rises, it cools, and it forms brand new oceanic crust, which creates those mid-ocean ridges. But this doesn't just happen in the ocean. On land, the same pulling apart force creates these enormous cracks in the crust that we call rift valleys, like the famous East African Rift, which, might one day actually become a whole new ocean. All right, let's head to our next stop. We're going to see what happens when plates aren't dividing, but are on a direct collision course. And I'm telling you, this is where we see some of the most powerful and dramatic forces on the entire planet. Welcome to a convergent boundary. Again, the definition is simple. Two plates moving toward each other. But unlike, say, a simple car crash, what happens when two continent-sized plates collide depends completely on what kind of plates they are. Yeah, it all comes down to the type of crust. Are we talking about a dense, heavy oceanic plate hitting a lighter, more buoyant continental plate? Or are two equally buoyant continental plates smashing into each other? Because the results are spectacularly different. And this slide just shows it all, doesn't it? On the left, you've got the Andes Mountains in South America. On the right, the Himalayas in Asia. Both are absolutely massive mountain ranges, and both were created by convergent boundaries. But they were formed by two totally different types of collisions. So let's look at the Andes first. This is an ocean-continent collision. The oceanic plate is way denser, so it basically can't win. It's forced to dive down or subduct underneath the lighter South American continental plate, and that process creates a super deep oceanic trench just off the coast, and it also melts rock deep underground, which then rises to form a chain of volcanoes, and that's the Andes mountain belt. Okay, now for the Himalayas. This is what happens when two continental plates collide. Neither one is dense enough to get pushed under. They're kind of like two equally matched sumo wrestlers. So there's nowhere for all that rock to go, but up. It buckles, it folds, and it thickens, creating the highest mountain range on Earth, and that vast high-altitude Tibetan plateau just behind it. Incredible! So we've seen plates pull apart, and we've seen them crash together. So what's the third option? For our final stop, we're visiting a transform boundary, where plates just try to slip right past each other. So at a transform boundary, crust isn't being created or destroyed. Instead, you've just got two plates grinding against each other as they move in opposite directions. But let me tell you, this movement is anything but smooth. And you can literally see the evidence of this grinding motion right here on the seafloor. This is the Mendocino Fracture Zone off the coast of the Pacific Northwest. It's just a massive scar on the ocean floor, and it's a direct result of this horizontal plate movement. And of course, California's famous San Andreas Fault is another classic example of this, but on land. The key features here are these huge fracture zones, along with these really distinct zigzags you can see in mid-ocean ridges. But because the plates don't slide smoothly, they get stuck. They build up immense stress, and then, snap, they release it all at once. This is what makes these boundaries absolute hotspots for tectonic activity, especially earthquakes. So, there you have it, a quick tour of the three main ways that tectonic plates interact at their boundaries. Now let's pull back and put all these puzzle pieces together to really see the big picture. This right here is the ultimate cheat sheet. You've got divergent boundaries, where plates pull apart, creating new crust at ridges and rifts. You've got convergent boundaries, where they push together, causing subduction that forms mountains, volcanoes, and deep trenches. And finally, transform boundaries, where they slide past each other, causing those fracture zones and lots of earthquakes. These three processes, they account for pretty much most of the major geological features of our entire world. And you know, the most incredible part of all of this? It's all still happening right now, right beneath our feet. The continents are still drifting, the oceans are still widening, and mountains are still rising. Our planet is this dynamic, living geological engine that is constantly remaking its own surface. Which, of course, leads to a pretty fascinating final thought. If these plates continue on their slow, relentless journey, what's our planet going to look like in the distant future, say 50 million years from now? Will new oceans form? Will whole continents collide? The story of our planet is still being written, 1 centimeter at a time. Thanks for joining this explainer.